Alright, let's do some more examples. First of all, I've seen the videos. I know the humming in the background with the AC unit can be really annoying, and so I actually tried to start doing this video without the AC, and it just did not work. So I'm sorry, but until it starts getting cooler outside in the evenings, I'm going to have to keep that thing on. Yeah, because otherwise the only other alternative is I open the windows and then you can hear people screaming outside, or even worse, the people outside can hear me talking about math, and that's no fun for anyone. So we're going to do just another example of some group actions. So let G be GLN C. So this is the collection of all n by n matrices with entries in C. These are matrices that are invertible, i.e. the determinant is non-zero. And we're going to let X be MNC. So this is just all n by n matrices with complex values. We don't care what the determinant is. It could be like a really messy matrix. It could be just a zero matrix. So we're going to let G act on X by conjugation, i.e. if we take a matrix G in GLNC and a matrix A in MNC, then this is going to be G times A times G inverse. So this is the group action, and this is matrix multiplication. So let's see here. This fixes determinants, traces, and eigenvalues. So this ends up being really nice. This fixes a lot of things. And this, did I spell this right? I don't know, probably, maybe not. But these facts, this is all just linear algebra stuff. The fact that G and G inverse are invertible matrices. And so actually, moreover, if A and B in X belong to the same G orbit, then they have the same characteristic polynomial. And that's, again, something that you can check. And from there it should be clear that, for example, the eigenvalues are maintained, because we use a characteristic polynomial to find out the eigenvalues. Okay, so now for another thing, and this is a little more. Now we're going to start getting into some more important group actions rather than just some miscellaneous examples that are sort of nice. So, just going to say fact. I don't know if, so we have many actions of G on G. And these end up being of particular importance, especially in some of the things that we want to prove. So let's look at an example of G acting on itself. So consider a map L that takes us from G to now remember one way that we could view group actions was a map that takes us from our group G to automorphisms of the set X. But here we're considering G as our set X, and so I'm just going to write automorphism, and I'm going to write set here just to make it clear that this is not a group automorphism. This is not the collection of group automorphisms of G. This is the collection of set automorphisms of G. That has nothing to do with the group action. It only has to do with the elements of our group G. And so LG is, so if you take L and we plug in G, we're going to get a map, and we're going to call it LG, where L sub G, and then if we evaluate this at the point X in G, this is going to be G times X, where this multiplication here is in the group G. So this is called left translation. And so this is a really important group action. Alternatively, we could have defined right translation, where instead of this map being multiplied on the left by G, we multiply on the right, but you have to be careful there, because it turns out if you look at the definition of a group acting on a set, if you want to multiply by G on the right, in order for it to be a group action, you need to multiply on the right by G inverse instead of G. And that's an exercise that you can do. That you can figure out that first of all, left translation is actually a group action, because I just told you that it is. I didn't prove it. But then if you replace, instead of having this be Gx, if you have it be X times G inverse, then that gives you a group action. And here's another example. And this one is also very important, and there's going to be a lot of definitions that go into this example. So we're going to consider a map C from G to, again, G. And here, of course, I still mean automorphisms on the set G, but I'm not going to rewrite that, because that's like 3 letters I could just not write. So anyways, C is going to map the element G to C sub G. And the map C sub G, if we evaluate this at X, this is going to be GXG inverse. So, let's see here. So it turns out that for all G and G, CG it's not just a set automorphism, but it's a group automorphism, and I'm just going to write ought there. I mean, maybe I ought to write the full thing out, but I only have so much space on the board. So, is this easy to see? So let's think about this. I realize that if I do this, then the sound goes from my paper all the way like directly into my microphone, so it sounds like I'm yelling, so I'll try not to do that. So if we consider this map that sends X to GXG inverse, then let's see here. So CG of, oh yes, it is, because CG of xy equals gxy inverse. But now what do we typically do? What's the trick that we typically use here when we're dealing with conjugation? You multiply by the identity, i.e. in between x and y, we're going to put g inverse g. And so now you should see, oh, now we're conjugating both x and y. And so this is going to be, as I run out of space here, cgx times cgy. And so that proves that this is actually a group automorphism and not just a set automorphism. But that's sort of something extra that we get in this particular example. That's not a property of group actions in general. I'm sure there's examples where you have a group action that does that is not a group automorphism. Like, I'm sure even just looking at left translation, you can come up with an example there. But I don't want to like stand here in front of the camera for 5 minutes and try to think of up an example, particularly if there's one that I could think up in like 3 seconds if I wasn't trying to teach stuff at the same time. Because teaching makes you think less good. So, anyways, we have this group automorphism here. Let's see here. So, the stabilizer. So, we're continuing this example. We're still talking about conjugation here. The stabilizer in G of an element X is going to be the collection of elements G such that Gx inverse is equal to X. And so another way you can write this, and this is something that I find a little more useful, is this is a collection of all G. The G, of course, is an element of capital G, the group G. If we multiply on the right by G here, we get Gx equals Xg. And this is defined as z sub g of x, and sometimes we won't write the g there. Which we call the centralizer. Centralizer of x. So the centralizer, if you look at this, what it says is the centralizer of x is the collection of elements of G which commute with x. Because that's exactly what this says here. Okay. The G orbits under this action are called conjugacy classes. Conjugacy classes. All right. What about G to the G? Remember, this is a collection of fixed points of the element G. And so this is going to be the collection of all x and G such that Gxg inverse equals x. And so we could also write this as the collection of x such that right. Okay, so So you wanna be careful. What you wanna get is from something like this to something like this. But I'm kind of using x and g in different ways in these two, so you have to be a little careful, because this is a collection of g's such that g x g inverse equals x. This is a collection of x's such that g x g inverse equals x. So if we want this to look like this, then the thing that's over here needs to be the thing that's doing the conjugating. So we need to have x's kind of sandwiching the g's. And so we can write this as x such that x g inverse x inverse equals g inverse. And is that obvious? X g inverse. Right, so you multiply on the left by g inverse, and that tells you x g inverse equals g inverse x. And then you multiply on the right by x inverse, and then you get x g inverse x inverse equals x times, or then on the right you'll have g inverse times x inverse, which is just g inverse. Okay? And so this is equal to this, which is, now this is the center of g inverse. So this is a collection of things. Right. So this is a collection of things that commute with g inverse. And let's see here. If xg inverse equals g inverse x, then multiplying on the right by g gives you this, and then multiplying on the left by g gives you this. And so what that shows is that this is actually the same thing as the center of g. And so in this case, the stabilizer of an element is the same thing as the collection of fixed points of an element. And that's just something that's special about conjugacy classes. Okay. Our counting lemmas, remember we have orbit stabilizer, and there's the other one, become, let's see here, so we have the order of g is equal to the sum over all alpha in squiggly c, which is the collection of conjugacy classes. And so here we're going to get the order of g divided by the center of x alpha, where x alpha is just some chosen element of this conjugacy class. And I guess we don't need a comma there if we're going to be super grammatically correct. And then the number of orbits, well, the number of orbits is just the number of conjugacy classes. So this is just squiggly c is going to be equal to 1 over the order of g times the sum over all g in g of the center in g of the element g. And this is just, we're plugging in the stuff that we've done before into those lemmas. Okay, so that wraps up all the important facts that we want to consider for now about the centralizer and about the group action of conjugation.